They're already starting to. It's making
Yeah,
it
turn
worse
the
today.
light.
Like, I don't know if you noticed, but last night it wasn't that bad. Today, the ice is terrible. Like, it's already starting to get worse.
All right, thanks for being able to making this class in a snowy day, icy road, and I know this class have, including the VLS as well, have giving you a lot of pressure, probably a lot of homework assignments compared to other classes. Is that true? It's been a lot, yeah. So at the very beginning, I just have to keep it rigorous. You know, it's genuinely these two classes are challenging everywhere, not just at Forest College. Even though we are a very small college, I still want to keep high standard. Don't want to teach the way that how my teachers taught when I was in college. I didn't learn anything. So the good thing is I'm not just a open loop system. I'm looking at your quizzes and homework assignments and all this performance over there, and surprisingly, you guys are doing so well. So I think I can keep doing the same way. Just kidding. Yeah, I'll slow down a little bit and see how things go. Okay, and you can see not just for you guys, it's the same for me. It's pretty much took me the whole day after every single class. It's from 8 a.m. Only 55 minutes for the class, but the rest of the day, including the meetings and everything else, I couldn't do anything else but just grading. I spent so much time on grading. So in the past, if I see, you couldn't see the numbers over here. If I see something like this in the past, I'll just give up. I usually will turn it back to you probably 2 weeks after turning it in. But after my sabbatical, since I had 100 students, right, the grading work is unbelievable. I mean, I just couldn't handle that over there. So after I came back, I appreciate this environment a lot. That's why I become so patient. I was like, oh, only 15 assignments? I can do it. So I was looking at every single detail about your homework assignment and grade it carefully. So that's why sabbatical is a good thing. Turning me into a better professor, I think. I'm feeling so grateful to be able to teach over here, not in mines. So you can see there's like 14 to grade, 12, 15, and I just spent the whole day yesterday to finish all the grading, but now there are another 3 assignments to grade. Okay, but I think I will, for example, I'm gonna slow down. If you look at the schedule here, I was trying to be a little bit more aggressive for the semester since I want to integrate the SOC design from that industry partner here. I'm just adding this material to this semester. But I feel that every tutorial, probably I should give it the whole week instead of putting them into 1 week. So that's what I'm doing now. I gave you a review session and I didn't cover any new things on Tuesday. And I'm trying to give you more heads up today to cover the logic design for the lab on Tuesday next week. So you have the time to digest the materials. And I will give you a little bit more review for the lab we did on Thursday last week because none of you have finished, I believe. I don't know. I mean, people didn't finish everything in the lab, so probably because the rolling display a little challenging. So you can take a look at more examples. And there's another thing I need your help, but I'm giving you some bonus points. If you're not able to finish one of the assignments in the past and losing points, so you can use this opportunity to get some bonus points. Become a great booster. It's this grant I got supporting some of the curriculum cost. Where is that? Did I post it? Assignment?
I don't know.
This one? Oh, it's not published yet. Alright, so the link is over here. Is a pre-survey, and there will be a post-survey after that project. So we are not adding. Oh, too small, right? But you can go to Canvas and look at it. It's a survey for a cultural. Adding some cultural contents to the project, to the computer engineering projects. Downplay, just make it less tedious, and make it more culturally relevant to your background. It could be any patterns you're interested in, and we can use that pattern instead of using a tedious basic storyboard image as our VGA project. So I'm definitely not changing a lot of things, because if they ask me to change more things, I will refuse to do this project. I don't want to take time for you guys to do engineering design. That's more important. So there's only one project you can see on the VGA during that week. I know a lot of computers don't have VGA ports anymore, but we are not using our computer's VGA port, because the basic storyboard has a VGA port. Even though it's already outdated, no too many people are still using that anymore. But learning the logic behind the scenes is still beneficial. Probably in the future, 2-3 years from now, I'm going to change it to HDMI. But now, let's still practice the VGA protocol. And you guys are actually going to implement a VGA controller into the hardware. Right? It's not a microcontroller. It's not just software and instructions. It's going to be a hardware. It's a chip. Okay, it's a digital module like this. Deal with all the bottom level logic sequence for the VGA communication. And eventually, the basic storyboard will be connected to the monitor in the lab. So I think all these have VGA ports still. Yeah, still have VGA ports. I'm gonna give one of each of you a VGA cord and connect to the monitor, and you can display a lot of interesting things. So instead of displaying, and you still have to run through all these experiments, right? Different a solid color, for the lab. One of the labs is showing a picture of the basic storyboard, and I think I'm gonna try to figure out a way to let you guys convert any images you're interested in, and convert into a digital image and send it to the monitor. Okay, but it have to be culturally relevant to your background.
Could I scan, like print it out, fill it out, and scan it and upload it? The assignment?
But it has to go through the FPGA board. So how to upload it, right? Upload it from the laptop. That's not a purpose, right? So it has to be.
No, the survey.
Oh, the survey. Yeah, of course. So the survey is assignment, right? Oh, you guys are interested in the points. I'm just kidding. Points are more important. Just get it done first. Talk about the images later. Yeah, which makes sense. So you know how that works? The 10 bonus points. So the base points is 0. So it's gonna be 10 out of 0. You know what I mean? If you don't do it, you're not losing any points. Okay. Make sense? Okay. Take probably 5 to 10 minutes in the class today to do the pre-survey, and after the VGA labs, we'll do a poster survey and see how that works. Okay. There might be some other requirements. I have to talk with the PI first and see if it has to be indigenous pictures and patterns, or it could be any cultural relevant patterns. I have to confirm with them. Okay, but do the survey first before we moving forward, and you can receive 10 points over there. And so now let's come back to our today's stuff. Okay, take a look at this one first. It's a combinational logic, and it's gonna let you practice truth tables and convert into a clocked circuit for the IPGA display. So the goal is to have a traffic light system. So without the microcontroller, there's no microcontroller involved, just the pure logic and clocks. So you have green, yellow, red, green, yellow, red. Inputs or outputs? 6 lights. It's a cross street.
This would all be out.
So it's just 2 traffic lights. Not dealing with 4, but should be equivalent, right? On the other way. So only 2 traffic lights, and these are outputs because they are directly connected to LEDs. Okay? And you need the inputs. How many inputs? We don't know yet. So the number of inputs depends on how many entries you have for the all combinations. Do you know how many entries you have? We are saying, hey, 6 digits is going to be 2 to the 6. Really?
It's a lot.
2 to the 6 is 64 combinations.
But we're not
It's going to confuse every single driver.
yeah.
You got 64 combinations.
Yeah.
It's difficult to remember, like which one to go where, right?
Yeah.
Okay, there will be like traffic lights to control dogs and cats and okay, there are limited number of combinations. What are they? For example, if this side of the road is red, it has to be green. Doesn't make sense if both are red.
Yeah.
Okay? And what's next? After a few seconds or a few minutes,
I guess.
the green one should become yellow.
Yeah. No, stay red.
Okay, stay red. And after, yeah, that could be another pretty interesting experiment. You know, sometimes on a very busy road, if you are turning left to the rec center, which is a dead end road, right? So it usually they will flash a yellow light instead of directly give you a green. So they want the main road to have more traffic during the rush hours. Okay, should I add a task 3 to the lab? No, you are good?
Yeah.
Yeah? Okay. What's next?
So green and red. So like green 1 and red 2.
So this one directly switch to where?
Green. That goes to red.
Wait, nope. It does have to be red at the first at the same time, right? For
Oh, yeah.
for a few seconds,
Oh, that's right. Yeah.
because someone was trying to rush through the yellow light,
Yeah.
which is everyone here.
Yeah.
So it has to be right at the same time for a few seconds first. Okay. What's next?
Then it's green.
Then it's okay to turn green. What's next?
Then yellow and red. Be red and red again. I think that's the loop, right?
Yeah, if it's not loop, what's the next?
The next would be red, green.
And you find out there's the same state. If I use this one, it's just creating an extra combination of the code. So there will be 2 different binary inputs to give the same binary outputs, which is really unnecessary. If you are using a simple counter, adding by 1, and eventually after this one it comes back to here, then it's going to create a time delay at this state because they're the same state. After it jumps back, seems like it's not changing.
Yeah.
It's increasing the time at this state, which is wrong, okay? Unless you need it. So we don't need it. And that's everything we need. Then look at the inputs. How many entries do we have? 1, 2, 3, 4, 5, 6. 2 bits?
Yeah.
2 bits? 6 states. Do you need 2 bits to resolve everything, or you need more bits?
I think we need 3.
You need the 3 bits because 3 bits can give you up to
7.
8 combinations, and you have 6. So it's good enough. just counting, okay? Since we know how to count it in the digital system, just add a 1 to it. When clock arrives, pause edge of the clock arrives, we add a 1 to it. It's really easy to loop through. So there's no necessity to have a microcontroller like CPU to handle it. Just adding 1 to it. It's a simple counter, okay?
It's gone.
Oh, it's very common. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1. Okay? So now let's design the logic. So every single output deserves a combinational circuit. So you want to look at every single column. Let's put it zeros in here first. That's it, right? What is the circuit for G1?
G1 is like what would the logic be for it? I guess it would be just equal to.
So there's only one here, right?
Yeah.
So we only need to look at this entry.
So it'd just be A naught.
0 1 1, so it's A naught BC.
Yeah.
For Y1,
That would be A B naught C naught.
mm-hmm. R1,
And A B naught C.
mm-hmm.
Oh, sorry, yeah, because there's that. Is that? Yeah.
Do you need to simplify these two?
Um,
It's unlikely, right? So red is the easiest, the shortest circuit you can have. Do you want to simplify this one?
yeah, that's.
Yeah, let's do it. Why is not 1 0? Why is 0 1? Why is 1 1? 0 0 0 1 1 1 1 0. Why is not 1 0? Why is skipping? Yeah, because the key map, every time you can only change one bit.
Yeah.
So 0 1 to 1 0, you're flipping both bits. So make it impossible to simplify. So you can only change one bit each time. That's how we simplify it. You can tell. So now let's see. After we put all these SOPs over here, you'll tell, right? So 0 0 0 0, 0 0 1, 0 1 0, 1 0 1. Okay, can we simplify?
Yeah.
The key map is just actually simplifying all the SOPs.
Yeah.
And the reason we want to put these two together is because we can group them. Okay, we can group them, and they will have at least the one common component, so we can factor out. That is why we can only flip one bit each time. Okay, so now see why we can group them, because you can see they have both zeros, which means they have both A naught, so we can factor that out to simplify. Okay. What else?
We still factor out the column. And then I believe you can do the 0 and the other side as well.
Right? So R1 equals what? Let's look at these two first. So these two items have a naught at the same time, so keep a naught here. And if you're looking at BC, C naught, because B is getting toggled. Okay, so it's cancelled. So C naught. It's gonna be A naught, C naught. Okay? For these two,
A naught and B naught.
because C is getting cancelled, it's getting toggled, so it's cancelled.
Yeah. B naught and C.
A toggle, so A is cancelled.
Yeah.
B not C. B not C. Okay? For this column. Right, so that's the final result. Keep doing the same for G2, Y2, R2. G2, Y2 are simple. R2 probably requires a similar process. Make a K-map, simplify it, get a final logic, so you can type it in Verilog. Make sense? And show you. This is a regular one, so when you are working on this, fill it up, have all these logic expressions for all these traffic lights, and put in your code. Okay, it's really simple. And for task 2, it's going to be a rush hour mode. We are keeping one of the traffic lights has a doubled period or duration here compared to the other one. So which means we assume one of them is during rush hour, right? So we keep one of them a little bit longer time. Basically doubled the previous time. So it's being controlled by a switch. We are assuming someone is able to control it somewhere remotely. Okay, so whenever one of the switches on the basic 3 board is getting switched on, the rush hour mode is on, so they won't have the same time delay. So one of the traffic lights, a set of the lights, will have a longer duration. Okay, so how do we deal with that? It's actually longer green, right? You are saying, hey, double the time for the yellow light. It doesn't make sense, right? So when you double, you want to make it longer, which means the green light is longer, so more traffic can go through. So which state we are actually trying to make it longer? It could be either green, right?
Yeah.
Doesn't matter which one.
Yeah.
So what you can do is just add one more state in here. Okay, since you want to keep it longer, so just don't change anything. You keep the same state, just duplicate it in here. However, your number is still counting, so after this one, you keep counting like 100, and this becomes 101, this becomes 110. It's basically just have this exactly the same state while this input is counting to another number, a bigger number here. Okay, there are many other solutions, but I think we can just use this solution for this lab, which is fine. It's the easiest. So if you're adding one more entry here in the middle, keep the same state, the same traffic lights, just duplicate the entire output to the next line, but input becomes 100 for that line, and all the rest should be increased by 1 as well. Okay, so in that case, you are having a different truth table. At least the columns are changing for several of them. You have to figure out which ones are changing and have different logic expressions for that new truth table. Okay, so you'll find out the new set of logic expressions you can put in the Verilog for the rush hour mode.
Okay.
But everything's within one digital module. You don't want to say like during the rush hour, I just unsolder every circuit and put a new circuit board in there every day, right? So it's basically everything's still in the same system. So you have to control it using a different mechanism. The switch is controlling that on and off. And so what you can do is have a different case. Okay, so you can see here, I give you example. I'm gonna update it because I don't see it in so many conditions. I think the second part is redundant. I'm gonna remove it and update the figure on the website. So you can see there's a one trick here, just in case you guys get stuck. So whenever I have a switch, let me draw it on the figure. Yeah, this is what I found out, but probably could be wrong. But I've seen this for so many times. So for FPGA top, right, I have switches from 0 to 15. All right, and you have a sub module. If you're trying to directly use that switch value here and use the wire, and you put that switch value into, for example, if statement, right, putting here, and that won't work. It's very interesting. So you cannot directly use the sub module and directly short it to the switch as a wire and modify, like use as a condition or use as a concatenation and shift it. I think I mentioned this briefly during the lab on Tuesday. So what you have to do is have a little buffer. So your switch, whatever, okay? So in your sub module, you have to have a latch to store that value. It's a register tab. It's a reg tab. And then the output of that reg tab can be used as a condition or a concatenation or shifting, whatever. So you can modify it. It has to be buffered. Keep that in mind. So if you come back here, let's take a look at the difference, right? Let's look at the difference. So this is the sub module. It's a traffic decoder. It's a traffic controller or decoder. Doesn't matter. Same thing. It's a traffic-like decoder. Okay. You can see which one is a switch. Which one is connected to the switch? Rush. Okay. Rush. That's a port. Rush input is not a port. Here's the port. Okay. So this one, in the instantiation of the top module, even though I don't have it here, you can imagine. Oh, one more thing to talk about. So, is the top module of the FPGA difficult to write up? It should be super simple, right? Especially for this one, only several lines. What are they? Don't get scared, because a lot of times in the past you are dealing with a simulation top. You are thinking, oh, top modules are difficult. You have to deal with all these time delays and all these initial begin and for loops. But for the FPGA top, it's just so simple. These are basically just a breadboard. Breadboard in the lab, right? You place the breadboard, you plug it in and probe it. That's it. So how do we do that? Just think about this system. Think about this system's ports. What do we do for the top? I can directly write it down here for you, okay? What are the ports? You don't even need to think about that too much. What are the resources you have on the board? Yeah, only switch and LEDs, right?
Yeah.
So switch is being used as what? The rush hour activation, right? Yeah, the toggle, okay? Input what?
Switches.
Just use all the switches. What about that? No one will blame you. It's okay. Just declare it, just in case. What else?
Inputs.
What else is the input? Clock, yeah, the onboard clock, which is 100 megahertz, is the input. What's the output?
Just the LEDs.
16 LEDs. And you don't even need a comma here. That's it, right? What else do you need? N module.
Yeah.
What else?
Under test.
Under test, yes. Instantiation, right? Instantiate that. So that name is like say traffic what? Decoder. And that's a UUT. That's a unit under test. Or DUT, device under test. Okay? So it'd be dot something, right?
Yeah. Whatever the input variables are. So,
Oh, we have a. Oh, that's the top. Yeah, yeah. So remember what I showed you here? The sum module has a rush input, has a clock, right? Okay. So you don't even need to think about it. The clock is always a clock. Just type this one first. You know it always is needed.
yeah.
You know, no brainer. Just type it. Dot clock. Okay.
Rush. Yeah.
Yeah, rush.
And then import the switches.
It has to be 1 bit, right?
Yeah.
You can pick up switch 0, switch 1, switch whatever. Doesn't matter, okay? What else? Outputs, LEDs.
Yeah. Dot LED.
Yeah, so what I did over here, you can see is light 1, light 2. Okay, so you can, so each light has 3 bits. So you can do this. Light 1 shorted to what? And I'll let you guys to do it. Light 2 shorted to what? So at the end of the parentheses, you don't have the comma anymore. So just directly this.
Yeah.
That's the whole thing for the top. So simple, right? The top is the easiest. Let's see. And then you figure out the rest. So you see the rush point, the rush input has to be buffered. That's what I was telling you guys. Okay? The rush has to be buffered. Because anything shorted to the switch or buttons or whatever on the board has to be buffered.
Yeah.
So that is why I have another register type, rush input, to handle that input from the switch. So the rush is directly shorted to switch by this. So there's no difference between rush and switch. It's just a wire. So it's directly making a wire connection between switch and rush. So basically rush is switch. So you cannot modify the keyword switch. That's why you cannot modify rush. So it has to be buffered. Modify means shifting, concatenation, or condition, even as a condition. It has to be latched by the flip-flop or register. So registers are usually flip-flops or latches. So you guys are in the outside, we'll learn that later, but if you're not, next semester we'll learn it. Next year we'll learn it. But eventually, it has to be latched. So the value is latched in order to get analyzed by the conditional statement, like if statements, like that. Okay, have to be latched. So that is why we need a buffer. So it's a similar technique. If you see the same issues for the 7-second display inputs, for example, you are using switches for that experiment, you need to know that. Okay, switches has to be buffered, right? See, that's the regular mode. Okay, I'm using switch 1, I think. And this is longer, right? Okay, that's it. Super simple. Okay. Let's see what else I'm going to cover. Okay, yeah, another one. So we have a quiz today. So I'm going to write you guys start working on the quiz 5 minutes from now. So what's going to be on the quiz is, I think it's really simple. It's a really short piece of code. Okay, so what you need to know is how to take the inputs, from switches and control the LEDs, and that's it. So it's a closed book, closed notes, and it has to be implemented on FPGA. Do you have your board with you?
Yeah.
Okay, cool. No? You have it, right? Cool, cool, all right. I'll give you 5 minutes to review all these top module, how to deal with the top module of the switch and the LEDs, or sub modules, how to program it, all the structures. And you can also take the 5 minutes to take a break. So when you come back, go to the quiz. Probably give you 20 minutes to do the quiz, and then after that, you can start working on your either whatever homework assignments or labs. You'll be free after that. Okay.
Actually, is it